what we'll do is to try to quickly go through some of the things that I've been doing as a review for some basic concepts underlying structural analysis. So once again, what we did over the last two lectures, sort of in a real, rather fast-paced, was to go through some of the concepts on what equilibrium for deformable bodies means. Uh, where do we get those equations that govern the behavior of beams? What does compatibility of deformations means? Uh, how does the material behave, and so on. So very quickly, I'll once again remind you that in terms of equilibrium for beams, what we really did was we said if we have a beam structure, something like this, some distributed load, some boundary conditions, then if you draw the free body diagram of a segment of the beam, then you can set up equilibrium equations for that structure. And this is a common theme across any type of structure. You want to set up an equilibrium equation, draw a free body diagram. Right? This is what we've always done. So looking at this free body diagram, what we did was we set up these two equilibrium equations, which is applied load is, or applied distributed load is the derivative of the shear force along the length of the beam, and the shear force is the derivative of the bending moment along the length of the beam. And using these two fundamental properties, you can very quickly draw shear force bending moment diagrams like we saw last time. Couple of key things that I mentioned about deformation and strains. I mentioned that in one dimension, the conventional definition that we use of strain is change in length over original length. But is that a good measure for strain? If you have a bar that looks like this black bar here, which extends to this blue bar, is that a good definition, change of length over original length? No, because it's an average measure of strain. Clearly, in this bar, which has varying cross-section, the strain will be changing from point to point. And the same story holds for stresses. Stresses also change from point to point. You can't say that this structure is under so much stress. No, this structure at that point has such and such stress is a more accurate statement. But if the section is uniform, then you can indeed use your average measure of strain, like change in length over original length. So I pointed out that truly what the definition of strain should be, it should be in terms of derivatives of displacement. If you know that the displacement is displacement as a function of x all along the length of this bar, then you can write the strain as derivative of that displacement. That's the better definition. And a similar argument holds in 3D, where the derivatives actually become partial derivatives in 3 dimensions, but essentially it's the same idea. And I mentioned that for beams, in particular, the most important measure of strain is curvature. For beams, what is curvature? I think this is an important point for us to talk a little bit more about. What is curvature? You might think that curvature is just m over ei, and it's true for linear elastic materials. Curvature happens to be equal to m over ei, but that is not the definition of curvature. The definition of curvature is this right here. Kappa, with whenever I have these 3 equal to lines, this means defined as, rather than just equal to. When I say 3 lines like that, we should read that as defined as. So curvature is defined as derivative of theta along the length of the beam. What does that mean? I pointed out last time that theta is nothing but the angle that the cross section makes with the horizontal. So if I have this beam and if I apply some loading to it and it deforms in this manner, then you can see that all these different cross sections along the length of the beam are remain straight, remain rigid before and after deformation, but they tilt. They tilt with respect to the horizontal axis, right? And that angle that they make with the horizontal axis is what is theta. And the rate of change of that theta is what is curvature. That is how curvature is defined. Um, I also pointed out that for beams that have negligible shear deformations last time, that this d theta over dx happens to be just the second derivative of the displacement. If you have a beam that maybe displaces like that, then you know what y as a function of x, that's the displacement of the beam along the length of the along its axis. So if you take the second derivative dy square over dx square, that happens to be curvature for beams that have negligible shear deformation. So I think that's something that I sort of quickly mentioned last time. And about where we were last time was this discussing this material properties. And I pointed out we'll restrict ourselves to linear elastic materials, where clearly strain and stress are related through the Young's modulus. And if you plug that relationship into the assumptions behind the beam theory, what we then obtain is the relationship for beams, that if you have some amount of curvature, the moment is related to the curvature using EI, that's the bending stiffness. And maybe one way to visualize this curve or this plot is this. If I have a perfectly straight beam, no moment anywhere, what is the curvature here? Zero. No moment, no curvature. If I apply some small moment at the two ends, M, right? What would be the bending moment diagram of this beam with M moment here and M moment here? Anyone? Just a rectangle, a constant moment throughout the length, right? M here, M here, it's a constant moment throughout the beam. What would be the curvature? M over EI. EI, if EI is constant all along the length of the beam, moment is definitely constant. If I apply M here and M here, moment is definitely constant, right? And if EI is also constant all along the length of the beam, then the curvature is also constant all along the length of the beam, which means that the rate of change of angle theta of all of these cross sections will be constant all along the length of the beam. So when I apply these two moments, carefully look at this beam. It pretty much looks like an arc of a very big circle, right? And in a circle, if you draw radial lines, the rate of change of angle of those radial lines is indeed constant. So that's what this material behavior, that's the material behavior that we are going to assume for our structures. That curvature is linearly related with moment. The more moment you apply, the more curvature you have, and the rate at which moment and curvature are related is the slope of that is the bending stiffness EI. Okay. Questions on this? So I know I'm going a little bit fast right now, but it's only because these are things that you already know. If there are any doubts, you got to stop me and ask questions. Okay. But we'll have plenty of opportunities to ask questions. So I think at this stage, I pretty much have all the tools I need to be able to solve a structural analysis problem. So I'm going to go ahead and state the final problem statement that we are going to try to solve. For any structure, whether it's a three-dimensional structure, complicated structure like that, or a simple beam structure supported like this, we are always relying on those four conditions or four concepts to try to solve such problems. Those concepts were equilibrium. For general three-dimensional bodies, I won't go into the details, but this equation this is a derivative of stress plus body force equal to 0. This is the three equations that I showed you for sum of forces in X, Y, and Z. Maybe I'll show you again. Right here. So these big complicated differential equations are actually represented very neatly in a vector format like this. So for general three-dimensional bodies, we do have an equilibrium, complicated differential equation that governs equilibrium. But for beam structures, beam and frame structures, equilibrium is much simpler. We already know that derivative of m equal to v. That was one of the one of the equilibrium equations we found. Another was the applied loading is dv dx. If you combine them together, assuming no shear deformation, then you can show that the governing equation of equilibrium for beams is d square dx square second derivative of uh, m. This entire thing is just m, right? Dy square dx square is curvature. Curvature times ei is the moment. Second derivative of moment has to be equal to the applied loading. That's the overall governing differential equation that we are trying to solve for beams. Um, so if I give you, or if whenever in the past in 371 or 270, if you have had a beam supported, say here and here, and applied some load here, essentially what you are doing by trying to solve that beam is to solve this equation. This is the governing equation where you're trying to find y, the transverse displacement of the beam all along the length of the beam. Okay, so um, in addition to that, we are using exactly the same concepts to solve any structure. Strain displacement relationships for 3D materials is again complicated, but for our case, we defined curvature as d square y over dx square. Material relationship again was complicated in 3D cases, but in our case, we are saying for beams, we'll relate moment, bending moment, with curvature using EI. That's the simple relationship for material material behavior that we are using. And if you combine all of these relationships of equilibrium, strain, stress, and material, you can express those relationships very nicely in this form. How many of you have seen this form before? Sigma or minus sigma over y equal to m over I. This part you must have seen, which you should have also used for your homework one, part B. And it's equal to the Young's modulus divided by the radius of curvature, which actually straight away follows from the definition of curvature. So this is a good thing to understand and to commit to memory, this relationship. And of course, this m over ei equal to d square y dx square, that's the governing equation that we are trying to solve with equilibrium. So at this point, we have all the relationships that we need to solve for deflections, to solve for shear forces, bending moments at any cross section in a structure, in a beam or frame type structure. Okay. So what we'll do is to try to calculate some of these deflections, see uh, how we can find deflections. So again, this is sometimes people use different sign conventions, but hopefully you've all been using this sign convention. On left side of a cut, again, maybe I'll take this beam example again. So this beam, if I draw the free body diagram of this beam under some loading, then you need to visualize half of this beam, that is your left side and the right side. And that's what I'm showing here up here on the screen. The left hand side, shear force pointing down is positive, bending moment in the counterclockwise is positive, shear force up and clockwise is positive on the right hand side. Another way to look at that is if you pick a segment of a beam, if you, again, under this loading, if I have this moment, this is a smiley face, of course, and means a positive moment, constant moment throughout the beam. On the other hand, if I apply moment in the other way, like this, that's a frowny face, and we have a negative moment, a constant negative moment throughout the beam. So in either of those cases, if you look at a small segment of the beam, That's what I've drawn up here. Curving upwards, curving downwards, positive and negative. And using these basic relationships, uh, we can get roughly what the deflected shape of structures should be like. So what we'll do is we'll do a couple of examples here, and looks like I should be in here. Um, calculating deflections, right? So let's do a couple of these examples, and then again I'll ask you to take a piece of paper, and this time I'll be sure to collect them at the end. Take a piece of paper, write your name on it, and part C and D I'll let you work on, and then turn it in at the end of the class. Okay, but let's go through and do part A and B first together, and then you can do C and D by yourself in a little bit. So how about part A? I have this beam, simply supported beam, two equal and opposite forces, P and P, acting up and down here. I want to find the shear force diagram, the bending moment diagram, and the deflected shape. So how should I go about it? What should I do first of all? Say it again. Reactions, yeah. So what would be the reactions? P and P here. What would be the reactions here and here? We don't know the magnitude just because we don't know the length of the beam and don't know the moment arm between this P and P. But let's say R, okay? Since this P is down, this P is going down, this P is going up, so the beam would try to rotate this way. And to oppose that, we would need to have a reaction pointing up here, a reaction pointing down here, some value R. Let me ask you this. Does it matter where in the beam these two coupled forces are applied? If I take these two coupled forces, let's say from here, and move them, does it change the reactions? Changes or no? How many say yes? Okay, how many say no? Yeah, so it doesn't change. Why? Why does it not change? What equation are we using to find the reactions? Right? Sum of forces and sum of moments. So clearly these two forces put together with some specified distance between, the same distance between them, as long as the distance between them doesn't change, the reactions won't change, right? Because the length of the beam is constant, so that would indeed be the reactions. Now, knowing that these are the reactions, what would be the shear force diagram? Do I need to take the long approach and try to figure out the shear forces and all that, or is there a easy way? Anybody want to give me? Go ahead. Yeah, go ahead. Tell me what the shear force diagram would be like.
Starts at a negative R.
Okay, it would go down just because I have a negative R here, so I'll have to go down by R.
And then is P greater than R?
Yeah, P will be greater than R because the moment arm between P is smaller than the length of B, right?
So P goes.
So yes, P would go up. It would go all across constant P, and so this is the value R or minus R here. This would be what P minus R up here. It would drop down again by P, go out here, and come back to 0 like that. Shear force diagram is that. How about the bending moment diagram? dV or dm dx is equal to the bending moment diagram, right? Dm dx is equal to the V, the shear force diagram. So derivative of the bending moment diagram would be equal to this. It's starting with 0. So it would go down out here, go up to this point, and go back down here. That's our bending moment diagram, right? Using this, can I draw the deflected shape? what should the deflected shape look like for this type of a bending moment diagram?
Negative curvature.
Okay, so indeed this would be a negative curvature, this would be a positive curvature, which means that if I were to, let me try to pick a thicker color here. So if I were to draw that shape, something like this is what we would have, right? Approximate deflected shape. Make sense? Any questions on this example? So this is again just trying to intuitively understand how we can quickly judge what the shear force bending moment diagram and deflected shapes would be like for simple structures. You obviously cannot generalize this technique for more complicated structures with complicated loading. But once you do have a bending moment diagram for complicated structures, you can draw approximate deflected shapes like that. Let's do another one. How about this guy? Say P1, there's a cantilever beam with P1 in the middle, much greater than P2 at the end. What would be the reactions for this? Whatever is the balance of P1 and P2 would be acting down here, right? All right, so let's mark that. Let me call that R1.
How do you know it goes down?
I said P1 would be greater than P2, right? So yeah, it has to be balanced by this reaction at this end. And how about the moment? Which way would the moment be pointing? Counterclockwise or clockwise? Clockwise. Why clockwise? Well, one way to think about this is that if this was not a fixed support and if this was not a free end, let's say if it was a simply supported beam and I had a big load in the middle, two equal loads at the ends, then this would want to curve up, right? If it wanted to curve up, and if I wanted to make the rotation at the left end 0, then I would have to apply a moment in the clockwise manner. Make sense? All right, so let's apply a moment in this way. Of course, I would need the values of the loads and the distances and all that to calculate the actual value of M. But here I'm just trying to show you intuitively how you can do these things. So once again, shear force diagram, go down by R1, go up by P1, crossover, sorry, solid line, and then go down to in this manner. So this would be P2. This would be R1 or negative R1. That's my shear force diagram. What would the bending moment diagram look like? What value would it start at 0? M, positive or negative?
Positive.
Positive. So it will indeed be positive. Let's say some value M starts here. Derivative of this is negative, so it would quickly go out to some value here, and then it would increase up to 0 out here. Make sense? Any questions on how did I do this? So once again, what I did really was there is this moment at the 0 at x equal to 0, which is clearly a positive bending moment. So I start with M. There's a negative shear force, so the rate of change of bending moment should be negative. It goes down to some value, and then the shear force is positive in this region, so it has to increase, and at the end it has to be 0. So that's how we quickly draw the bending moment diagram. And how about the deflected shape? What would the deflected shape be like? Right, so just follow the curvature. If we see that this is positive curvature, this is negative curvature all the way throughout, then the bending moment diagram would be something like, oh, sorry, the deflected shape would be something like where only in this region where there is positive moment, we have the smiley face for the curvature. And everywhere else in this region, this entire region, we have a negative uh, moment. We have a frowny face for the deflected shape and the curvature. Make sense? Any questions before we jump into the assignment in class activity? No? All right. So please do take a piece of paper, write your name on it. Try to attempt parts C and D, and make sure you turn it in at the end of the class. So take maybe, I'll say, 3 or 4 minutes. After that, you can discuss it with your left or right neighbor, and then we'll do it together in class. Again, this is not a quiz. I'll go around and maybe Wei, you can also go around, and if somebody has questions, you can definitely ask us. This is not a test. Equilibrium, right? So if you want moving equilibrium, what should the direction of the reactions should be? There's only one force on that. Draw the Freeburg diagram, right? And then there's only one moment on the beam. So yeah, so to counter it, what should be the direction of the reactions? Oh. That was stupid. All right, let's take maybe another minute or so, and then you guys can discuss amongst yourselves. All right, go ahead. Feel free to discuss with your neighbors, see if you both got the same shear force, bending moment, and deflected shapes. And then we can go through it together.
This one's under 10 minutes. This is a correction. It is. You know how fun it is when the one camera is smarted? It will never happen again. No, because it's free. It's free. It's free. Yeah. And there's no moment here, so the book's just
All right. Let's see. What did we find out? Is is this structure determinate? Yes, clearly. It's almost a simply supported beam. How about this guy? D is definitely not determinate. So you will have to make some engineering judgments or guesses to be able to solve that part D. But we'll go through it together. How about this first part C? We have this beam, simply supported beam with two overhangs. I have a moment out here. So to counter the moment, I need to have reactions the other way. Reaction R down here, up there. And the value of R, of course, depends upon the distance between the supports and the applied moment. If this is the reactions, then what should be the shear force diagram? What should the shear force diagram be? Starting with, go ahead. Okay, so which means that through this length and through this length, it should be 0, right? So we'll do that. 0 out here. Actually, I'll draw a solid line. Drop down to minus R. Be constant minus R. Go back up and be 0 throughout here. Question?
How do you know which reaction acts up and down? Because usually there are more reactions up and down.
Okay, so how do we know whether which reaction is going to be up, which reaction is going to be down? Go ahead.
You know, because you need to resist the moment with the moment couple.
Right. So, for example, here, if I remove the supports, then I have this beam which is being acted upon by a moment. And to counter that moment, I have these two reaction forces, and I need to make sure that they are in the right direction, which is just another way of saying equilibrium. Right? Sum of moments has to be 0. That's why the reactions have to be pointing that way. And if ever there is a doubt, just go by equilibrium, Newton's laws, right? Newton's laws cannot go wrong. You cannot go wrong by doing that. It might be a slightly longer approach. Draw the free body diagram, assume the reactions, set up equations of equilibrium, and you'll see that the reactions come out that way. Okay. All right. So if this is the shear force diagram, what would the bending moment diagram be? What value does it start at? Positive m, right? So, and out here it's positive m, and does it change? It remains constant all through this length. It's only when the shear force becomes negative that it drops down to 0, and it again remains constant out here, 0. That's the bending moment diagram, which means that the deflected shape would be like what? What would the deflected shape be like? Right. So indeed, it would mostly be positive curvature since the bending moment. Oops. Okay. The bending moment is positive. The curvature would be positive, and let's see. So together with the boundary conditions, we can draw the deflected shape like this. And I think this is too steep here. Maybe I'll make it shallow. Two questions here. Is the curvature in this middle section changing? Curvature changing in that middle section? Yes, because the moment is decreasing from some value down to 0. So the curvature is maximum here and it is decreasing down to 0 here. How about the curvature in this half? There's no curvature, it's straight. So indeed, I would need to draw that as a straight extension all the way there. And how about curvature in this half or this 1/3 of the beam? Curvature would indeed be constant because the bending moment is constant and curvature would be positive. So on the left side of that middle segment, we would have the beam curving upward. Sorry, it's not, there's not too much space out here. Otherwise, I'm just exaggerating the curvature here. That's why it looks like there might be a kink here, but of course there's no kink here, right? So this is the deflected shape for this part. Key things here would have been to notice that this right third of the structure remains straight and the left third is still curving. Okay. How about the last part? Any questions before I go to the part D first? Any questions on this part C? No? Okay. All right. So how about this part D? First job, to find the reactions. Of course, this is indeterminate, so we cannot find the reactions just by using statics. In which case, either you can go to the force method by assuming a certain reaction and then enforcing that the displacement. So, for example, you can remove this support. Now it's determinate. You apply an unknown force here to try to make sure that the displacement at that point is 0, and that's basically what the force method is. But we'll learn all of that later. Right now, we are trying to do is to intuitively understand how things would behave. So, for example, in this case, what would be the reaction here? Why would it be 0? Right. So essentially, this load is being carried by this right half of the structure. This part is an internal hinge. When it deflects, the left half deflects along with it as a rigid body. So since there is no force, there are no external forces on the left half of this body, there would be 0 reaction out here as well. Okay. There would be some unknown reaction. I'll mark it as R here, maybe R1. And there will be some unknown reaction at the right end as well. Can anybody maybe just from engineering judgment guess which one would be greater, which would be pointing which way? So let me call this is R1. This should definitely be pointing up. I hope that's that's something that's clear. How about this guy? Would it be pointing up or down? Down. Why down?
Because it's resisting it.
Right. So if this support was not there, this load would want to make this go up, which means that this support is trying to push this down. Any guesses on which one would be greater, R1 or R2 in magnitude? R1 looks like, yes, I would agree. It looks like it would be greater. But again, that depends upon the lengths of those segments and the actual loads applied, which you would need to solve exactly to judge more accurately. But here, once again, we'll make these assumptions and go forward. So with this, we can draw the shear force diagram. And that looks like 0 all the way here, drop down by P, go up to R1, go up by R1 and then drop down to R2. So this is R2 which is equal to R1 minus P. This is minus P. That's the shear force diagram. Does the presence of this internal hinge affect anything in my shear force diagram? The internal hinge does not affect shear, right? It just transfers shear, whatever it is. It does affect the moment. Moment has to be zero at internal hinges. So how about the moment? Bending moment diagram, what would that look like? In all of this part, all the way up to here, it has to be zero, right? Okay, so let's mark zero bending moment all the way up to here. Shear force is negative at that point. So we'll go down by some amount, and then shear force is positive. It goes up. Would it go to zero?
No.
No. And I should have actually marked the bending moment out here as well. Some bending moment out, some reaction moment out there, and that would be the positive moment M that we have out here, right? Make sense? Yes? No? All right, so another thing to notice here is that we have this point where the bending moment goes to zero. What is that called? Point of inflection, where the curvature changes from positive to negative, right? How about this guy? I have this beam. How many points of inflection do I have here? One, right? On this side, the curvature is positive, smiley face. And on this side, the curvature is negative. So indeed, there is one point of inflection, which is the point where the moment changes sign from positive to negative, where the moment goes zero, which helps us draw the deflected shape. So the deflected shape for this guy would look like, indeed, it has to be zero slope out here and positive smiley face curvature out here. At this point, it needs to reverse curvature, and it needs to have it needs to go down to zero at this point. So it would be this way, and it would be a straight segment here, and it would be a straight segment here. Make sense? Sorry, not at this point, but it would be, I need to extend that. I think something like that. So indeed, at this point, where at this point, sorry, again, so I think maybe what I'll do is draw it again. I'll delete that, and at this point it needs to go to zero, so something like that, and the slope is too sharp. It would be something like that. Okay, any questions on roughly trying, well, looks like some people are not sure. Any questions on roughly trying to guess what the, or draw the deflected shape? No? Okay, so hold on to your pieces of paper. At the end of the class, I'll collect it. I'll quickly go through this example of the method, really where we try to find the displacements exactly. So one of the ways to do structural analysis is simply by solving the governing differential equation, right? So can anybody tell me, how do we solve a differential equation like this? That's right. So how do you solve any differential equation? You just integrate it, right? And there's different ways of integrating those equations. But essentially, if we are doing structural analysis by solving differential equations, what we do is integrate the differential equation. So if this is the differential equation that we are solving, all we need to do is to integrate this twice to get y. What is y? The deflection. It is the transverse displacement of the beam. That's what we are really trying to find. We are trying to find deflections of the beam. So if we integrate this equation once, we get m over ei dx integral. Anything else we get? Do we get anything else? Indefinite integral means there has to be a constant of integration, right? So indeed we will get plus C1. How do we determine that constant for integration? Boundary conditions. So every structure has to have boundary conditions, either fixed or simply supported or something that will tell us how to find the C1. If you integrate it again, you get m over ei dx. I'll integrate the constant here again. So let me write that in C1 x plus C2. And that would be basically the simplest way to try to find deflections of any structure. If you know what the bending moment diagram looks like, M, you divide it by EI, which EI could be changing along the length of the beam, doesn't matter. You M over EI would be the curvature all along the length of the beam. So from the bending moment diagram, draw the curvature diagram and integrate the curvature diagram and use boundary conditions to find those two constants. That's basically what this double integration method is. Okay. I don't have time to go through this example here, but we'll do that next time. And I guess since Monday is a holiday, we'll meet again on Wednesday. Just as a quick reminder again, homework 1, part 1 is due today at 5 p.m. For part 2, which is due on Monday, all you need to do is to take your own homework 1, look at the solutions that will be available at 5 p.m. today, compare your solution versus the posted solution, and look at the homework guidelines for more discussion on what you need to do for part 2. Okay? If you have any questions, post them on the Blackboard discussion forum, and I'll see you back on Wednesday.